This lecture continues our discussion of user-defined types in the Oracle world. In our previous video, we introduced the concepts of behavior and the various types of methods that are available. In this current video, we'll examine the constructor method in some detail. The emphasis will be placed upon user-defined constructors and the ability to incorporate integrity within the behavior of the constructor. We'll also address an overloaded constructor and the benefits provided by being able to overload the constructor. The system-generated constructor is referred to as the attribute value constructor. This was initially introduced to us when we discussed the concept of creating a type that had only structure. We didn't specify that there were any methods, and the system supplied this constructor method for us. Even if we're creating our own methods, if we have member methods and map methods and so forth, we're not obligated to create our own constructor. The system will still generate an attribute value constructor for us. But we also have the ability to define our own constructor, what is referred to as a user-defined constructor. So the attribute value constructor is convenient to use because it already exists. But user-defined constructors have some advantages with respect to things such as type evolution. In particular, the attribute value constructor requires a value for each attribute of the type, while a user-defined constructor can be customized to require only some attributes. We'll discuss this point and provide an example later in this presentation. When you invoke the constructor, preceding the call to the constructor with the new keyword is optional. Oracle recommends that, and I suppose it makes sense because it makes it very clear to anyone reading the code that you are instantiating a new object, therefore new precedes the invocation of a constructor. As I just noted, there are advantages of user-defined constructors. Here we identify some of these advantages. A user-defined constructor does not require that you explicitly set a value for every attribute of a type, unlike the requirement in the attribute value constructor. A user-defined constructor can have any number of arguments of any type, and these do not have to map directly to the attributes of the type for the object being instantiated. When you define a constructor, you can initialize the attributes to any appropriate value. We'll see that the constructor will contain assignment statements whereby we would take the value that was passed as an argument and assign it to an attribute. Additional assignment statements can be present within the body of the constructor. These do not have to take the values provided by the caller or the invoker. For any attributes for which values are not supplied, the system will initialize these attributes to null. Furthermore, if the type is modified in the future, if it undergoes what is called type evolution, such as adding an attribute to the type, calls to user-defined constructors for the type do not need to be changed. Note, however, that user-defined constructors are not automatically modified when the type evolves, so their signatures will remain the same as when they were defined. You may, however, need to change the definition of the constructor if you want the new attribute to be initialized to something other than null. A user-defined constructor is defined in the type body in a manner similar to that of defining a member function. It must also first be announced within the type specification. That is, we'll see the announcement in the create type statement and the full body code within the create type body statement. The declaration of a user-defined constructor begins with the keywords constructor function. The function must return self as its result. It must actually say return self as result. This requirement ensures that the most specific type of the instance being returned is the same as the most specific type of the self argument. This will become important when we look at inheritance and subtyping. Just as with the attribute value constructor, a user-defined constructor must have the same name as the type. The constructor has an implicit first parameter called self. You don't need to specify self in the declaration, but if you choose to specify it, it must have a parameter mode of in-out. The function body must include an explicit return statement. Unlike other functions that you might write that will return some expression, the return statement simply includes the word return with nothing following it. What happens is the system will automatically return the newly constructed self instance. So you simply say return, and that's the end of the statement. A user-defined constructor could be implemented in PLSQL, C, or Java. We'll be using PLSQL to be consistent with our overall presentation. When a constructor is called, the system initializes the attributes of self, the object being constructed, to null. Names of the attributes subsequently initialized within assignment statements within the body of the constructor method may be qualified with self. This is useful to distinguish them from the names of the arguments for the constructor function if they happen to be the same names. User-defined constructors are not inherited, thus they cannot be overridden. A user-defined constructor hides and thus supersedes an attribute value constructor if the signature of the user-defined constructor exactly matches the signature of the attribute value constructor. This is an important point to keep in mind when you're creating the user-defined constructor. If a type evolves by adding an attribute, the signature of the type's attribute value constructor changes. So this can cause a formerly hidden attribute value constructor to become usable again. But a user-defined constructor does not automatically evolve. A user-defined constructor is called like any other function. We note that parentheses are required in SQL, even for calls to constructors that have no arguments. This is consistent with the syntax that we explained in the previous video for invoking a method from within an SQL statement. In PLSQL, parentheses are optional when invoking a constructor that has no arguments. Again, this is consistent with our previous explanation. However, using parentheses might be beneficial, making it clearer or more obvious that the constructor call is a function call. A user-defined constructor cannot occur in the default clause of a create or alter table statement, but an attribute value constructor can. So these are some important differences between the system-generated attribute value constructor and a user-defined constructor. You'll want to consider these when you're designing your object type and then preparing to use it. We revisit our address object type. Here's the create statement that includes the declaration of a member function named getCity, the comparison function, which is a map member function called compare, and finally, the introduction of a user-defined constructor. The arguments of this user-defined constructor are named and positionally ordered the same as the attributes for the type. Hence, this user-defined function would effectively replace the system-generated attribute value constructor. Notice again that in the create type statement, even though we're generating the constructor, we are simply announcing it. This is a forward declaration or presenting the signature. The details as to what exactly will happen within this user-defined constructor will be coded within the instructions as part of the create type body statement. If we now describe the address type, we again see the structure, the attributes, we see the other methods, and then if we continue, we'll see the result of the method included here. So it tells us the details that this is a constructor function, and it returns self as a result. It also shows us the argument list for this user-defined constructor. Note the parameter mode shown in the column labeled in/out. This has a value of in for each of the parameters or arguments to the constructor function. No explicit mode was indicated in the create type statement. The default mode is in. In general, this is how a function should be defined to avoid possible side effects. A little more of the metadata. If we examine user method results for our address type, we again see get city and compare as previously defined, but we also now see address listed as the third method because it was defined in that position. And its result type is address, an object type of address. Looking at user type methods for the address type, we see that address has 5 parameters. We had just examined the structure and noticed that there were 4 parameters listed: street, state, city, zip. But what we find is there is a 5th. Remember that self is passed as an input parameter as well. This is counted among the parameters here. This is what brings the total to 5. When we examine the parameters, looking at user method params, we do see self listed here. And notice that self is listed as the first parameter, and it has a parameter mode of in/out, and the parameter type is address. When coding a user-defined constructor, specifying this parameter in the declaration is optional. However, if you do choose to make this explicit, then you must declare self as in/out, as indicated here. When a constructor function is called, the system initializes the attributes of the self argument to null. The names of attributes subsequently initialized in the body of the function may be qualified with self, such as self.name. This may be useful to distinguish the names of the arguments of the constructor function from the names of the attribute of the object being instantiated, should these names be the same. If they're different, then we don't need to use self as a qualifier at all. The function body must include an explicit return. The return keyword must not be followed by a return expression. We made this point previously, but it's good to restate that, reinforce this idea. The system automatically returns the newly constructed self instance. That's why we see out within the parameter mode. Let's resume our examination of the address object type, incorporating the information we just presented. Here is the create type body statement. With the implementation of getCity, we see that we're returning city. We can simply say return city. But remember that the function, when it's invoked, will be invoked within the context of the self object. So it is also possible here to say return self.city. The map member function, labeled compare, returns a simple character string. Here we're returning the value of the zip code attribute for the invoking object. So once again, this could have been expressed as return self.zipcode. Notice in each case we have functions, and these functions are returning an expression. Now let's examine the constructor function. The constructor function, again, is declared as constructor function, and the name is the same as the object type, address. We list the arguments to the function, and we conclude the declaration of the header for the function by saying return self as result. Within the body of the function, because the arguments passed to the function have the same names as the attributes of the object being created, we're qualifying the attributes with self. Self.street will be assigned the value of the street argument passed to the function. Self.state will be passed the value of the state argument passed to the function, and so on. Finally, we conclude, once we've assigned all of the values and the object has been instantiated and initialized, to pass that object back to the invoker. And we do this with a very simple return statement. Notice that in returning the instantiated object, we simply say return. We don't return anything as we did in the other functions. There is no expression to conclude the return clause, as there was with the other two functions. A reminder that when a constructor function is called, the system initializes the attributes of the self argument to null. Here, we pick up from that point and assign the values of the parameters to the attributes of the object. With the general concepts of a constructor explained, we now turn to a little bit deeper explanation of constructors and how they can be used to add integrity for objects that we create. If we store an object in a table, we can use declarative or procedural integrity mechanisms to ensure the validity of these attributes. In the case of declarative integrity, we might have a constraint that says unique, not null, or something of that sort. This works well for objects that are persistent. However, such mechanisms apply only to that target table. Furthermore, if we were to use procedural integrity, say DML triggers, again, the trigger is associated with a specific table. We could extend this a bit if we took procedural integrity and enforced it through an application. If we wish to store objects in different tables, the tables are going to require the same integrity constraint mechanisms, whether those be declarative integrity or procedural integrity. This results in duplication of effort. Additionally, not all instantiated objects will be made persistent. We can use an object type for a variable. This would be a temporary or transient object. These objects are never given persistence. They are created within the working storage of an application as that application runs, and when the application terminates, these objects cease to exist. So what we really need, if we're addressing integrity, would be to incorporate some kind of integrity mechanism at the object level rather than at the table level. We can achieve this by incorporating integrity in the constructor of our type. With our address object type, we redefine our constructor function. What we're going to do is take the argument value that was passed to us and interrogate it. For example, let's look at the zip code. Suppose there's a business requirement that says the zip code must be 5 characters. That being the case, we examine the zip code that we received as an argument, and if its length is not 5, it's unacceptable. So we throw an exception. We call raise application error and return an error code. Because this check is performed within the constructor, it's performed when the object is instantiated, not when the object is stored. And what happens if the value supplied causes this exception to be thrown? The object will not be instantiated. Remember that when you use declarative or procedural integrity, it's tied to a particular table. However, we can combine these techniques. In addition to enforcing integrity within the constructor when the object is instantiated, we can also use declarative or procedural integrity in combination with that for stored or persistent objects. If we now attempt to instantiate an address object where we did not abide by the rule that the zip code must have 5 digits, the constructor will throw the exception. Here we're attempting to create an address object with only a 4-character zip code. The result will be the constructor receives this value in the zip code argument, says it's not the proper length, and throws the exception by calling raise application error. The application attempting to perform this insert receives an error that says invalid zip code, and it gives us the error message, ORA minus 20000. It turns out that this error message and this error number were the arguments that we passed to raise application error. So if you're not acquainted with the use of raise application error, what happens is when we throw that exception by invoking raise application error, the message appears to have been generated by the Oracle database system. It has an ORA error number, and we can handle this just like any system-generated error. We're now going to make a significant change to the object type. I want to comment that before we discuss this code, you have to consider if you're making a significant change to the constructor or to the structure in terms of attributes of an object type, you have to consider the impact on existing instances of the object. So before we can run the create or replace type statement to add an overloaded constructor, we'll need to remove the addresses table, which holds instances of this type. We do this by issuing a drop table statement, drop table addresses. In practice, we would not want to drop a dependent schema object such as a table. The proper way to deal with this is through type evolution. For now, our attention is on illustrating behavior. We'll consider type evolution at a later time. I wanted to make that point clear that we can't just jump from where we were to what I'm about to show you. When you declare a formal in parameter, you can specify a default value, in which case the parameter is referred to as an optional parameter, which means that when you invoke this constructor, you don't have to provide a value. If the actual parameter is omitted, the invocation of the constructor assigns the default value to the formal parameter. Note that a formal parameter that has no default values is called a required parameter. The way we achieve the default value and an optional parameter is by using an overloaded constructor. We start with our first constructor, which has all of the attributes. This is the same constructor we've seen before, but now we add a second constructor. So the code that I'm showing you here has been extracted from the create type statement for the address type. Now, here's the second constructor. This is the one that has only 3 attributes: street, city, zip code. State is not specified. We cannot provide a state value through running of this constructor. Notice the comment says that state has been made an optional parameter. Now let's move to the create type body statement and see the details of how the constructor operates. We've retained the integrity check for the size of the zip code. Following that, we'll take the street value that has been passed, assign it to self.street. The city value, assign it to self.city, and the zip code, assign that to self.zip code. Nothing has changed there. But notice the assignment to self.state, nothing was passed in. There is no state argument. So we hard-coded the value here. This is the default value. The addresses will all be within the state of Connecticut. This is an overloaded constructor because we now have two definitions of the constructor function named address. Having dropped the addresses table, we start over by creating the table as a collection of address objects. We insert into addresses the result of invoking the address constructor with 4 attributes. Here we're providing a street, state, city, and zip code. In the second insert statement, we're invoking the overloaded constructor. Notice that when we call address, we're providing only 3 values. The values we're providing will be the street, the city, and the zip code. We're not providing a state value. Therefore, due to the difference in the signatures, the system recognizes you're calling the other constructor. You're calling the overloaded version. This is the same as in object-oriented programming languages, such as Java or C++. Let's examine the result. If we go to the database and query the addresses table, 2 row objects are returned. And notice the one for Windsor Street has a value of Connecticut. This was not supplied by invoking the constructor and giving it a value for the state, but this is the default value. So what have we addressed? We explained the differences between a system-generated constructor and a user-defined constructor. We identified advantages of a user-defined constructor, why we would want to go through the effort of creating one of these, what does it offer us, and there were several advantages that we pointed out to suggest that it might be a very useful feature. We examined the metadata related to user-defined constructors. We examined the same views we had looked at previously, but we examined them within the context of a user-defined constructor. We explained how a user-defined constructor could provide integrity when we instantiate an object. And finally, we discussed optional parameters and default values for attributes of an object type. In our next video, we'll be discussing additional types of methods. We'll be considering the comparison methods and the member methods.